Okay, good morning. Today we are going to study about transformers. That means practical transformers on no load condition and what are the relations and voltage current relationships on load condition. Okay, so a practical transformer, we have to consider two cases when such a transformer is on no load and also when it is loaded. So first we are going to consider on no load condition. On no load condition, no load means there is secondary is open. This side is open. There is no load connected on the secondary side. So here is only the V1 voltage applied on the primary side, and there will be a current that is taken as I0. I0 means it's a no load current coming from the primary side. And now we are assuming that on which there are no core losses and copper losses. Okay. On ideal cases. In the previous classes we assumed that an ideal transformer. For the simplification, first നമ്മൾ assume ചെയ്തത് അതൊരു ideal transformer ആയിട്ടാണ്. On that condition we assume that there is no core loss and copper losses. But in practical condition it is not possible. There will be some core loss and copper losses. So we have to modify that characteristics from the ideal transformer. That means for an actual transformer, there will be some losses. Okay. When it is put on load, when we connect a load ZL on the secondary side, there is iron loss in the core and copper losses in the winding also. So there will be more current. So we have to consider the copper loss on the winding also. First നമ്മൾ condition on no load condition, when it is an actual transformer there will be core loss, and when it is on loaded we have to consider the copper loss of the winding also, because current flowing through the winding will increases when it is loaded. In no load condition I0 is very small current as compared to load current, but there will be some small winding copper losses is also present in no load condition also. But in loaded condition there will be a current I2 on the secondary winding. Therefore an extra current I1 has to flow through our primary winding. So I1 will be more than our no load current. So if more current is there, copper loss, I square R loss will be high. That means there will be we have to consider the copper loss also. Okay. So now we are going to consider the no load condition. Okay. No load condition. When the transformer is on no load, the primary input current is not wholly reactive. The primary input current under no load condition has to supply iron loss in the core. That means what is iron loss? Iron loss means hysteresis loss and eddy current losses. So when there is no load, then also the primary current has to supply some losses in the transformer, that is core losses. കോറിൽ ഉണ്ടാകുന്ന ലോസസിനെ സപ്ലൈ ചെയ്യണം. നമ്മൾ കൊടുക്കുന്ന ഇൻപുട്ട് വോൾട്ടേജ് കാരണം അതിൽ പ്രൊഡ്യൂസ് ചെയ്യുന്ന കറണ്ട് I1ന് കോറിലുള്ള ലോസസിനെ സപ്ലൈ ചെയ്യണം. കോറിൽ എന്തൊക്കെ ലോസസ് ആണ് ഉണ്ടാവുക? We have already told the properties of a ferromagnetic material in which hysteresis and eddy current. So there will be these two properties produces some losses in the core, that is hysteresis loss and eddy current loss. So a very small amount of copper loss is also present there in the primary winding. Okay. Then no load primary current, we represent it as I0. No load primary current I0 has to supply what? No load primary current has to supply that hysteresis and eddy current losses. And copper actually the copper loss is very negligible. So we take it as purely reactive. So hence no load primary input current I0 is not 90 degree behind voltage but lags by an angle phi which is less than 90 degree. Okay. So when we consider there will be some copper loss and iron loss, core loss will be there. Okay. In a actual transformer, when we apply a voltage on primary winding, there will be a no load current I0. That I0 has to supply two components, copper loss and core losses. So when we draw a phasor diagram, there will be voltage phasor diagram and it is the relationship of voltage and current when it is on no load condition. So the primary what will be the primary input current, input power W0. We just consider at no load condition the input power of the transformer is the input voltage into the current, no load current, and cos phi 0 is the power factor. Vi cos phi ആണ് നമ്മൾ represent ചെയ്യുക. So cos phi 0 is the no load power factor. Okay. So no load power factor actually ഒരു large value ആയിരിക്കും because the magnetizing component of the current will be very high as compared to our resistive component. So there will be large angle between voltage and current. Lagging angle will be very large. So no load power factor is very high. Okay. So actually the primary current I0 has two components. One component is in phase with V1. Okay. So next we can draw the phasor diagram on no load condition. No load phasor diagram of a transformer. Okay. In no load phasor diagram, we just assume voltage angle as in the vertical angle. Okay. That is, we assume V1 on the vertical angle as a reference, and we know that the flux produced in the transformer will be in the will be perpendicular to this, and current will lag behind the voltage by what? 90 degree. Okay. So if it is a purely magnetizing component. So actually the I0 has two components. Okay. One is in phase with the V1. So one component will be in phase with the V1 and one component will be quadrature with V1. So no load primary current I0 has two components. One is in phase with V1. This is known as active component or working component. So we represent it as IW, active component or working component. What is the purpose of this working component? We call it as active component of working because it is mainly supplies the iron loss plus small quantity of primary copper loss. Hysteresis and eddy current lossന് supply ചെയ്യുന്ന componentനെയാണ് നമ്മൾ iron loss component or working component എന്ന് പറയുന്നത്. So we can represent it as which is in phase with the V1. So we can write IW is equal to equation എന്തായിരിക്കും in phase component ആയിരിക്കുമ്പോൾ which is I0 cos phi 0 എന്ന് represent ചെയ്യാം. And one component is in quadrature with V1, that is known as magnetizing component. So it's represented as I mu. Magnetizing component is represented as I mu, which is in quadrature, and because its function is to give magnetize the core, that means its function is to sustain or maintain the alternating flux in the core. So it is magnetizing component, that means purely reactive component. So I mu will be always perpendicular to V1 and we can represent it as I0 sin phi 0. So what will be the total current, total no load current in a primary winding? Obviously I0 is, we represent it as I0. So I0 is the vector sum of these two, this vector sum of IW and I mu. So we can write it as IW square plus I mu square, or vector sum of these two values. So how can you find out the vector sum? So this will be our I0, this I0. Okay, so we can represent it as I0 as a vector sum of IW and I mu. Okay, so then we have to note the no load primary current I0 is very small as compared to a full load primary current. When it is loaded, this full load primary current will be increased. And also if I0 is very small, no load primary copper loss is also negligibly small. So that no load primary input is practically equal to iron loss in the transformer. So we can consider that copper loss is negligible on the primary side when it is on no load condition. ലോഡ് ഒന്നും ഇല്ലാത്ത കണ്ടീഷനിൽ നമ്മുടെ കോപ്പർ ലോസ് നെഗ്ലിജിബിൾ ആണ്. കാരണം ഒരു ചെറിയ കറണ്ട് പ്രൈമറി വൈൻഡിങ്ങിലൂടെ ഫ്ലോ ചെയ്യുന്നുള്ളൂ. സെക്കൻഡറി സൈഡ് ഓപ്പൺ ആണ്, സെക്കൻഡറി സൈഡിൽ കറണ്ട് ഇല്ല. സോ പ്രൈമറി സൈഡിൽ ഒരു ചെറിയ കറണ്ട് മാത്രമേ ഫ്ലോ ചെയ്യുന്നുള്ളൂ. അപ്പോൾ പ്രൈമറി സൈഡിലെ കറണ്ട് നമുക്കാണ് ഈ പ്രൈമറി സൈഡിൽ കറണ്ട് കൂടുതലാണെങ്കിൽ ആ വൈൻഡിങ് I2R ലോസ് കൂടുതലായിരിക്കും. ബട്ട് on open circuit condition there is no load in this side. There is no load in this side, so there is no current in the secondary, so only small current to magnetize the core is there, so I2R loss is less. So we can consider that copper loss is negligible, so no load primary input is practically equal to iron loss in the transformer. Okay, then okay, actually we can when we represent the transformer in an electrical manner, there will be a primary winding and a core and a secondary winding. Okay, so in this portion core, what are the losses in that core? There will be some losses in the core due to hysteresis and eddy current. Losses are represented as a purely resistive component, that is R0, and to magnetize the core there will be some magnetization losses that can be represented as X0. So in the core itself there is some losses as a magnet, iron loss and copper loss. Okay, so due to actually this resistive loss on the core is not wholly eliminated. By laminating the core we have reduced into its negligible value by laminating the core. കോറിൽ വരുന്ന റെസിസ്റ്റീവ് ലോസിനെ നമ്മൾ റെഡ്യൂസ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് കോറിനെ നമ്മൾ ലാമിനേറ്റ് ചെയ്തിരിക്കുന്നത്. സോ R0 എന്ന് പറയുന്നത് വെരി നെഗ്ലിജിബിൾ വാല്യൂ ആയിരിക്കും. ആൻഡ് X0 ഇസ് ദ മാഗ്നറ്റൈസേഷൻ ലോസസ് ഫ്രം അയൺ ലോസസ്. ഓക്കെ, so there will be these two components. So we can represent the core as a parallel branch like a resistive component and a reactive component in it. Okay, so when we represent the primary winding you have to consider the core losses as R0 and X0. We can represent the core. Okay, മനസ്സിലായോ? അതായത് നമ്മൾ കോർ എന്ന് നമ്മൾ മാഗ്നറ്റിക്കലി റെപ്രസെന്റ് ചെയ്യുന്ന ഈ ഒരു പോർഷനിൽ വരുന്ന ലോസസിന് നമ്മളൊരു ഇലക്ട്രിക്കൽ റെപ്രസെന്റേഷനിൽ we consider it as an R0 and X0, reactive component and resistive component which is connected in parallel to the primary winding. Okay, so we can represent the winding. And also in practical condition in a transformer there will be primary winding resistance and winding reactance. You have to consider winding reactance, that is if it is a primary winding R1 and X1, and we consider the core resistive property and reactance property in parallel to this branch. Okay, and the ideal portion of the winding is I just represent like this. Okay, actually core is there, the property of the core is shifted to here, and the ideal transformer winding I again representing here, and the secondary winding will also have resistive property, winding resistance and winding reactance. So practically there will be R2 and X2. In the initial condition we consider an ideal transformer without any losses. So we applied a voltage V1 here, and a current will flows through the first condition when there is no load. What happens when at the no load condition there is no current in the there is no current in the secondary winding, and the current flows through the primary is only to magnetize the core. So I0 will flows to the core only. Okay, only to magnetize the core. Okay, that is the first current when we apply a voltage V1 on the primary side. Okay, then when we connect a load on the secondary side, ZL, what happens? There will be a current flow through the secondary winding, that is I2. When we apply a voltage V1 on primary, it will produce a flux on the primary side. That flux will link with the secondary also, and that means it induces a EMF E1 in the primary winding and mutually induced EMF in the secondary winding. So when the circuit is closed by connecting a load, there will be a current flow I2. Okay. When a current I2 is produced in the secondary winding, what happens? When a current flowing through the coil, it produces a flux. There will be another flux phi 2 on the secondary winding. That flux will interact with the initial flux on. Initial flux is phi 0. ഈ phi 0 നുമായിട്ട് നമ്മൾ പുതുതായിട്ട് പ്രൊഡ്യൂസ് ചെയ്ത phi 2 interact ചെയ്യും. So there will be a flux phi 2 which is equal and opposite to phi 0. So it will try to, the flux produced in the secondary will try to kill the flux on the primary. So we have to overcome this situation. So it produces an extra current I2 dash on the primary winding when it is loaded. നമ്മളൊരു ലോഡ് കണക്ട് ചെയ്ത് കഴിയുമ്പോൾ പ്രൈമറിയിൽ ഈ ഒരു കണ്ടീഷൻ, phi 2 will try to oppose the primary flux. To overcome this situation, the primary winding produces extra current which is known as I2 dash, that is counter or anti current to eliminate this property. So the secondary MMF try to kill the flux on the primary winding. So to reduce that effect, the primary winding produces an extra large current I2 dash. So when consider this I0 plus I2 dash will give the total current I1. So the total current I1 coming from this primary winding is I1 coming from is the sum of core current, this no load current I0 plus an extra current produced in the primary when it is loaded. So I1 എന്ന് പറയുന്നത് it is a vectorical sum of I0 plus I2 dash ആയിരിക്കും. മനസ്സിലായെന്ന് വിചാരിക്കുന്നു. ദാറ്റ് മീൻസ് നമ്മളൊരു ട്രാൻസ്ഫോമർ ഫസ്റ്റ് ലോഡ് ഇല്ലാത്ത കണ്ടീഷനിൽ കൺസിഡർ ചെയ്യാം. നമ്മളൊരു വോൾട്ടേജ് അപ്ലൈ ചെയ്യുന്നു ഓൺ ദ പ്രൈമറി സൈഡ്. ഇറ്റ് വിൽ പ്രൊഡ്യൂസ് an EMF on the primary winding, that is self-induced EMF E1, and the flux produced in the primary winding will be linked with the secondary winding. It produces an induced EMF in E2. ഇനി നമ്മൾ ലോഡ് കണക്ട് ചെയ്യുവാണെങ്കിൽ it is a closed circuit, this secondary side. When a closed circuit is there, current will flow through it. I2 will flow through the secondary winding. We assume I2 is the secondary current. So when a current flowing through the secondary winding, it produces a flux on it. That extra flux will link with the primary also, but the produced flux will opposes the primary flux. So it tries to kill the flux. So primary winding has to overcome this situation. So it produces an extra current, that is I2 dash. So when the transformer is on loaded condition, primary current will increases to I1. So I1 is the vectorical sum of I0 plus no load current plus load component of current I2 dash. Okay. So ഈ ഒരു കണ്ടീഷൻ ഓർത്തിരിക്കും. So when we have drawn the no load characteristics like this, V1 and how the V1 and I0 related with this. Always know that V1 and I0 will not be perpendicular to each other. There will be some resistive component and magnetizing component in the primary winding. So I0 always lags behind the V1 because inductive property is the dominant property in a transformer winding. So current lags behind the voltage by an angle which is less than 90 degree. Okay. Now we are going to study the on-load condition. Okay. Transformer on-load condition. Phasor diagram. Okay. So we have drawn the almost equivalent circuit of a transformer on load condition. We have considered resistive, reactive drops here, R1, X1, R2, X2. But when we draw a phasor diagram, first we are assuming that there is no winding resistance and no magnetic leakage reactance. അതായത് ഈ രണ്ട് കമ്പോണൻസിന് നമ്മൾ ഫസ്റ്റ് കൺസിഡർ ചെയ്യുന്നില്ല. അതായത് R1, X1 and R2, X2 just for കൺവീനിയൻസിന് വേണ്ടി മാത്രമാണ്. ആക്ച്വലി ഇറ്റ് ഇസ് പ്രസന്റ്. പക്ഷെ നമ്മൾ ആദ്യം എങ്ങനെ അസ്യൂം ചെയ്തത്, നമ്മളൊരു സർക്യൂട്ട് ഫസ്റ്റ് ട്രാൻസ്ഫോമറിന് സിംപ്ലിഫൈഡ് ഫോമിൽ നമ്മൾ ഓരോ പ്രോപ്പർട്ടി ആയിട്ട് പഠിച്ചു വരുമ്പോൾ അതിലെ ചേഞ്ചസ് നമ്മൾ ഫേസർ ഡയഗ്രത്തിലൂടെ ആഡ് ചെയ്യും. പക്ഷെ ഫസ്റ്റ് നമ്മൾ അതിനെ ഐഡിയൽ ട്രാൻസ്ഫോമർ ആയിട്ട് അസ്യൂം ചെയ്തു. ദെൻ നമ്മൾ അതിനെ പ്രാക്ടിക്കൽ ട്രാൻസ്ഫോമർ ആയിട്ട് കൺസിഡർ ചെയ്തു. അതിൽ ഇത്രയും കമ്പോണൻസ് ഉണ്ട് എന്ന് മനസ്സിലാക്കി. നൗ ഫേസർ ഡയഗ്രാം ഓൺ നോ ലോഡ് കണ്ടീഷൻ പഠിച്ചു. ഇനി ലോഡ് കണക്ട് ചെയ്യുമ്പോൾ അതിൽ വരുന്ന ഡിഫറൻസ് എന്താണെന്ന് നോക്കും. പക്ഷെ ലോഡ് കണക്ട് ചെയ്യുമ്പോഴും നമ്മൾ അസ്യൂം ചെയ്യുവാണ് വൈൻഡിങ് റെസിസ്റ്റൻസിനെയും റിയാക്ടൻസിനെയും നമ്മൾ ഇല്ല എന്ന രീതിയിൽ. എന്ന് വെച്ചാൽ നമ്മൾ നെഗ്ലക്ട് ചെയ്തിട്ട് വാട്ട് ഇസ് ദ change or modification on load condition in the voltage and current എന്ന് മാത്രം നോക്കുകയാണ്. Then we consider winding resistance and reactance. മൊത്തമായി ആദ്യം കൺസിഡർ ചെയ്യുമ്പോൾ അതൊരു കോംപ്ലിക്കേറ്റഡ് ഡയഗ്രാം ആയിട്ട് തോന്നും. പക്ഷെ നമ്മൾ ഓരോന്നോരോന്ന് സ്റ്റെപ്പ് ബൈ സ്റ്റെപ്പ് ആയിട്ട് കണക്ട് ചെയ്യുമ്പോൾ you will get a clear idea. Okay. So now we are going to draw the phasor diagram of transformer on load. Okay. On load condition phasor diagram. Transformer on load phasor diagram. So first നമ്മൾ no load condition എന്താണ് അസ്യൂം ചെയ്തത്? When we draw a phasor diagram, voltage in a perpendicular direction and flux in this direction. Before that I will again explain one thing. We here consider the V1 in this direction. The induced EMF will E1 in the primary winding will be equal and opposite in this direction, and also E2 produced will be also we assume in this direction, E2. Okay, according to number of turns the magnitude will be different, E1 and E2. Okay, so now we are going to consider transformer on load condition. When we connect a load on the transformer, നമ്മളൊരു ലോഡ് കണക്ട് ചെയ്യാണ്. that load will be depend on that characteristics will depend upon the characteristics of load. This voltage current relationship will depend upon the characteristics of load. ഈ ലോഡ് എന്ന് പറയുന്നത് എന്താണ്? നമ്മളിവിടെ ഒരു ZL എന്ന് കാണിക്കുന്നില്ലേ? ഈ ZL എന്ന് പറയുന്നത് either it may be a resistive load or maybe a inductive load or maybe a capacitive property load. So it may be either pure resistive property or pure inductive property or pure capacitive property. ഏതെങ്കിലും ആവാം. ഈ ലോഡിൽ ഏതെങ്കിലും ഒരു പ്രോപ്പർട്ടി ആയിരിക്കും ഡോമിനന്റ് ചെയ്ത് നിൽക്കുന്നത്. നമുക്കറിയാം if it is a resistive load, voltage current relationship എങ്ങനെയാ വരിക? voltage and current are in phase എന്നാണ് നമ്മൾ represent ചെയ്യാൻ. If it is a resistive load, we represent voltage and current are in phase. If it is an inductive load ആണെങ്കിലോ voltage and current are, if it is a pure inductive load, voltage and current are lagging. Current lags behind the voltage by 90 degree. Lagging നെ നമ്മൾ 90 degree clockwise directionലാണ് represent ചെയ്യുക. If it is a capacitive load, voltage and current relationship will be like this. Current will lead the voltage by 90 degree. അങ്ങനെ മൂന്ന് പ്രോപ്പർട്ടീസ് ആണ്, ഡിഫറെൻറ്റ് പ്രോപ്പർട്ടീസ് ആണ് റെപ്രസെൻറ്റ് ചെയ്യുക. സോ the voltage current relationship will depends upon the characteristics of load, if it is resistive, inductive or capacitive. Okay, if the current I2 is I2 will be, that means the current I2, here it is I2 is the current which is flowing through the load. So current I2 is in phase with V2 if the load is non-inductive, and if it lags if load is inductive, when it leads if the load is capacitive. അപ്പോൾ ഒരു ലോഡ് കണക്ട് ചെയ്യുമ്പോൾ ഈ മൂന്ന് പ്രോപ്പർട്ടി നമ്മുടെ മൈൻഡിൽ ഉണ്ടായിരിക്കണം, if it is resistive or inductive or capacitive. Okay, now we are going to draw our phasor diagram. We are assuming reference phasor V1. Okay, first we are assuming V1, and also നമ്മളിപ്പോൾ കൺസിഡർ ചെയ്തിരിക്കുന്നത് എന്താണ്, ഈ R1 one second. R1 X1 ഈ പ്രോപ്പർട്ടീസിന് നമ്മളിപ്പോൾ assumed as it is negligible, that means we assumed that V1 is equal to E1 എന്നാണ് assume ചെയ്തിരുന്നത്. So we are not considering the magnitude difference in V1 and E1 or drop നമ്മൾ consider ചെയ്യുന്നില്ല. So we are going to draw V1 in this direction and flux in this direction. First no load conditionലാണെങ്കിലും എന്താണ്, on load conditionലാണെങ്കിലും there will be a current I0. So we have to draw first I0. We have already studied how to draw I0 like this. So and also in on load condition there is another current I2 dash also, and I1 is the vector sum of I0 plus I2 dash. So you have to draw these two. So first you have to consider I0. We know that there is a component which is in phase with working component, and one is I mu magnetizing component here, and the total current on no load is I0. I0 is the current, no load current. Now we are assuming that the induced EMF in the secondary is E2. E2 and E1 are in equal. We are assuming E2 is equal to first you assume the transformation ratio N2 by N1, N2 by N1 is equal to 1 and assume cheyana. Then you can assume this magnitude as equal. V1 E1 എന്ന് പറയുന്ന E2 എന്ന് പറയുന്ന മാഗ്നിറ്റ്യൂഡിനെ ഈക്വൽ ആയിട്ട് എടുക്കാം. അതായത് V1 ന് ഈക്വൽ ആയിട്ട് നമുക്കൊരു ഇൻഡ്യൂസ്ഡ് EMF E2 റെപ്രസെന്റ് ചെയ്യാം. ഓക്കെ, first we are assuming if transformation ratio ചേഞ്ച് ചെയ്യുന്നതിനനുസരിച്ച് magnitude of induced EMF high or low ആയിരിക്കാം. പക്ഷെ now we are assuming N2 by N1 our transformation ratio as 1. Okay, now we are going to represent the current. The current produced in secondary will be either in phase or lagging or leading depending upon the load. So first നമ്മൾ resistive load assume ചെയ്യാം. So our load is resistive. We are assuming our load is purely resistive. So what happens? The current produced in the secondary I2 will be in this direction, which is in phase with the E2. So we know that when the current I2 is produced, the similar current, this equal and opposite current will be produced in the primary to nullify the flux phi2. ഈ phi2 നെ റിമൂവ് ചെയ്യാൻ വേണ്ടി പ്രൈമറിയിൽ ഉണ്ടാവുന്ന കറണ്ട് ആണ് I2. അത് ഈക്വൽ ആൻഡ് ഓപ്പോസിറ്റ് കറണ്ട് ആയിരിക്കും ആസ് കമ്പയർ ടു ദ സെക്കൻഡറി കറണ്ട്. എങ്കിലേ ഈ ഫ്ലക്സിനെ നമുക്ക് റിമൂവ് ചെയ്യാൻ പറ്റുള്ളൂ. അപ്പോൾ നമ്മൾ പ്രൊഡ്യൂസ് ചെയ്യുന്ന പ്രൈമറി എക്സ്ട്രാ പ്രൈമറി കറണ്ട് എന്ന് പറയുന്നത് ഈക്വൽ ആൻഡ് ഓപ്പോസിറ്റ് ഡയറക്ഷനിലായിരിക്കും, വിച്ച് ഇസ് I2 dash. Okay, I2 dash. So I2 will be in this direction, I2 dash will be equal and opposite to our secondary current ആയിരിക്കും. So നമുക്കറിയാം I0 that you know that here you can see the total current coming from here is split into these two, I0 and I2 dash. So total current I1 is the vector sum of I0 and I2 dash. So we can find out the vector sum. Vector sum എങ്ങനെ കണ്ടുപിടിക്കുക? നമ്മൾ I0 ന്റെ I2 dash ന്റെ vector sum കണ്ടുപിടിക്കണം. So vector sum can be found out by drawing a parallelogram. So this diagonal will give you the I1. So this is the current I1 when it is loaded on a pure resistive load. Now we are consider an inductive load. Inductive load. When the load is inductive, what will be the difference? You again draw voltage phasor V1 and the flux phi on this direction and the current. Now I am not considering the current, magnetizing current and working component. You know that the current I0 will be like this. The vector sum of magnetizing current and working component. This will be your I0. And an induced EMF in secondary will be considered as equal and opposite to V1. Okay. Now, when the load is inductive, we know that current lags behind the voltage by an angle. So we consider a current on the secondary current I2 lagging angle will be represented in clockwise direction. So your I2 you consider which is in clockwise direction from E2, that is I2. Okay. Also you remember the I0 is very small as compared to our loaded current നെക്കാളും very small value ആയിരിക്കും. അപ്പോൾ നമ്മൾ അതിനെ represent ചെയ്യേണ്ട ഒരു ചെറിയ phasor ആയിട്ട് represent ചെയ്യാവും I0 നെ ട്ടോ. I0 ന്റെ magnitude വളരെ കുറവായിരിക്കും as compared to I2. When we consider the load current as 10 ampere, no load current I0 will be only 0.2 0.3 ampere will be there. So we have to consider the magnitude as smaller. Then I2 is the current flowing which is if a load is inductive, I2 lags behind E2 by an angle. Okay, now the extra current produced in our primary winding I2 dash will be equal and opposite to I2. So we can represent I2 dash like this, I2 dash. Okay, I2 dash can be represented equal and opposite to I2. Now we can find out the vector sum of these two. Vector sum of these two will give you what? This will be your I1. This will be your I1. Current flowing, the total current flowing in the primary winding I1 is the vector sum of I0 plus I2 dash. So now what happens? The angle between V1 and I1 is phi1. Here there is an when it is reactive, your angle will be phi1 here. Here it will be increased when it is inductive load. When it is inductive load, so power factor will increases. Now we consider when the load is capacitive. Okay. When the load is capacitive, the diagram will be just V1 and phi and the current flowing through the no load current I0 and induced EMF will be E2 and The current flowing through the secondary winding will lead when it is capacitive load. നമ്മൾ capacitive load ആകുമ്പോൾ നമ്മൾ leading angle ആണ് consider ചെയ്യുക. Leading angle will be represented in anti-clockwise direction. So I2 will be in this direction. The extra current on primary will be I2 dash. So the vector sum of these two will give what? I1. So you can see here the angle between V1 and I1 will be reduced. That means power factor can be improved by adding a capacitive load. Okay. So now we have considered without winding resistance and leakage reactance. So you have to now we are going to consider winding resistance. What happens when we consider the winding resistance? We have winding resistance and leakage reactance. When we consider R1 and X1, the V1 and E1 will not be equal. You have to consider the drop I into R1 plus JX1 drop will be there. You have to consider that also. Okay. And here also E2 and V2 will not be equal. Here you know that V1 will be greater than E1.